In this video, I'm going to go over the analysis of a three-phase rectifier with a load that's represented by a resistor. And the purpose of this analysis is to figure out what the output voltage waveform looks like, as well as the order or sequence in which these 6 diodes conduct. And to start off with, we have three line to neutral voltage sources, VA, VB, and VC, that are with respect to the neutral voltage. And we have that VB is lagging VA by 2 pi over 3 or 120 degrees, and VC is leading VA by 2 pi over 3 or 120 degrees. And these three phases are inputs to our three-phase rectifier, which consists of 6 diodes. And these diodes will conduct with a certain sequence to provide an output voltage, Vout, that contains a DC component. And this DC voltage is then delivering power to our load. So to start off our analysis, we want to gain some intuition for how these 6 diodes work to rectify the AC voltages. Let's start off by looking at the top 3 diodes, D1, D3, and D5. Now, the inputs to D1, the input is VA, the input to D3 is VB, and the input to D5 is VC. Now, it turns out that these 3 diodes are going to pick off the maximum of VA, VB, and VC, and this node is going to be the maximum of VA, VB, and VC. Now, let's think about why this is. Let's assume at a given moment in time, we have that the B phase is the maximum. So that means VB is greater than VA, and VB is also greater than VC. So we have that B is the maximum in this case. Now, let's assume for some reason that that D3 is not the one that's conducting. So let's assume that D3 is an open. And let's assume that VA is conducting, D1 is conducting, I'm sorry. So if D1 is conducting, that means that this node will be VA, but we know that VB is greater than VA. So that means that D3 actually should be conducting because VB is greater than VA and the diode will get forward biased. So that leads to a contradiction because then VA and VB are shorted to each other. So that's not possible because that would violate KVL. So in this case, this goes to demonstrate that D1, D3, and D5 conducts whichever one is connected to the maximum voltage of VA, VB, and VC. And therefore, the result that this node is the maximum of VA, VB, and VC. So now, if we look at these bottom 3 diodes here, D4, D6, and D2, they're going to play a similar game here. So we're going to have this node is VA, this node is VB, and this node is VC. So it's going to, because it's connected in reverse, we will have this as the maximum of negative VA, VB, and VC. Sorry, they all have negative signs. You can also think of this as the minimum of VA, VB, and VC. So therefore, these diodes will work to provide this node as the maximum of the negative line to neutral voltages, and this node will conduct to provide the maximum of the positive line to neutral voltages. And as a result, the overall Vout, which is the difference of these two nodes, so if we called this Vx is the maximum of the positive, Vy is the maximum of the negative. We have Vout equals Vx minus Vy. So at any given instance, the output voltage of the three-phase rectifier is going to be the maximum of all 6 combinations of line-to-line voltages. So that means we're going to have VAB as well as VBA. So it's going to choose the maximum among these, as well as VAC and VCA, and VBC and VCB. So essentially, this rectifier has the following function. The diodes will turn off in an order such that at any given moment in time, we're going to have the output voltage equal the maximum of all 6 possibilities of line-to-line voltages. So the next step of our analysis is to draw the output voltage waveform. And the phasor diagram representation will be a helpful tool for us. So we're given that we have the positive phase sequence, which means that if VA is Vm sine omega t, then VB is going to be um, uh, VA delayed by 120 degrees or 2 pi over 3, and VC is going to lead VA by 120 degrees. Now, in the United States, if you have a nominal 120 volts RMS um, line to neutral voltage source value, then Vm is going to be the peak value, which is just square root of 2 times the RMS value of 120. So we want to start off by drawing a phasor diagram for our 3 phases. So we're going to do that by drawing the complex plane. And it's going to be helpful to split up the complex plane into divisions of 30 degrees or pi over 6. So we're going to draw out these pi over 6 lines. So this is now our phasor diagram. So it's important to keep in mind that we can draw our voltage sources as vectors in our complex plane. And the value of these voltage sources is going to be the projection of these vectors onto the real axis. So let's start off with VA. So VA is going to be drawn with a vector that looks like this. So VA is Vm sine omega t, and we're drawing this phase diagram as a snapshot where omega t equals 0. So in this snapshot, VA, which is sine omega t, is this vector here. And this makes sense because if we project this onto the real axis, which is just going to give us 0, which is the same as sine 0 is 0. Now, if we were to um, spin this phasor around counterclockwise, later at omega t equals pi over 2, VA is going to land right on the real axis, giving us 1. So this is the accurate representation of sine omega Vm sine omega t. Now for VB is delayed by 2 pi over 3. So that means that it's going to be represented by a phasor that looks like this. So this is VB. And VC is leading VA by 2 pi over 3. 2 pi over 3 is 120 degrees. So it's going to look like this. So these are our 3 phasors for the line to neutral voltages. And they have magnitude Vm. So the lengths of each of these vectors will be Vm. Um, So the next step is we want to figure out the magnitudes and the angles of the line-to-line voltages, which are VAB, VBA, VAC, etc. And to do that, we will use some basic geometry. So if we have, um, let's say, VAC, what does VAC look like? Or sorry, let's start by looking at VCA. So it's just going to be if we draw the line from here to here with the arrow pointing in this direction, this is just going to give us VCA. So this vectors don't have any position in space, so we can just shift it up like this in parallel. So this is our VCA. Now, likewise, for VBC, let me get rid of this. VCA, and one more thing is that when we did that math there, um, if you do the trigonometry out, we know this is Vm, this is Vm, and this angle is 2 pi over 3. So just by doing the trigonometry out, you'll find that this value is square root of 3 over square root of 3 times Vm. So all the line to line values are going to be square root of 3 times the line to neutral values. So I can write an expression like square root of 3 times V line to neutral equals square root of equals V line to line. All right, so let's continue drawing out the rest of our vectors. So VCA here, we have a magnitude of Vm square root of 3. So the next one is VBC. So if we draw VBC out, it's going to be a vector like this. So that means if we just shift it here, this is VBC. And then we also have VAB. So VAB is going to look like this here. So this is VAB. And we can likewise extend it, shift it over in our plot, and this is VAB. So we have VAB, VCA, and VBC. And to find VAC from VCA, it's just going to be the vector that's directly opposite it. So VAC is just going to be the same direction, but in the opposite way. It's VAC. Likewise, for VCB is going to be opposite to VBC. So this is VCB. And likewise, opposite VAB is VBA. So this is VBA. So we have drawn out the 6 line-to-line voltages using our line-to-neutral voltages. So the next step is to draw out the waveforms, the sinusoidal waveforms of these line-to-line voltages. So to help us plot, we're going to want to plot a whole period. So from omega t equals 0 all the way up to omega t equals 2 pi. And to help us plot, we're going to want omega t tick marks um, um, at pi over 6 intervals. So we're going to have pi over 6, pi over 3, pi over 2. We're going to then get 4 pi over 6, 5 pi over 6, pi. Likewise, so on. We're going to get 3 pi over 2, and then 3 more tick marks to get us to 2 pi. And for our tick marks on the vertical axis, we're going to get one at 0.5 and one at 1. So this will likewise be the same on the negative side. So now we want to draw out, so if we have this is square root of 3 Vm, square root of 3 Vm over 2. And likewise, this is negative square root of 3 Vm and negative square root of 3 Vm over 2. This is our omega t axis. And this here is 0 in time and magnitude. So we're going to start off by drawing the sinusoidal waveform for VCB. And we see that VCB is starting off at its peak value. So it's going to have a peak right at omega t equals 0. Then it's going to decrease as so. So this here is our PCB. Next, we will draw VAB. So VAB is delayed by pi over 3. So at omega t equals pi over 3, it's going to reach its peak value. So this here is our VAB. Let's draw this. VCB is here. And yeah, let's keep that. So the peaks will label. So the next value is VAC. So VAC is going to reach its peak at 2 pi over 3. So that means it's going to reach its peak right here. So then we're going to get here, here. So next up is VBC, and we once again shift over by pi over 3 the peak from the last peak. So you can see we've hit VCB, VAB, VAC, and now we're at VBC. So it's the whole pi shifted from our original VCB. So we can start to see the pattern actually. So we're eventually we have that we're looking for V out, which is the maximum of all the line-to-line voltages. So we can just keep the pi over 3 peaks. So that's all we need to draw. So this is going to be VBC. Yeah, we've figured out the pattern. So this allows us to extend our analysis from the other curves. VBA. And then lastly, we have VCA. So we've figured out the waveforms for our line-to-line voltages. And because the output voltage of the three-phase rectifier is picking out the maximum of the line-to-line voltages, we've found that it's just going to take on the maximum of these peaks. So it's going to give us an output voltage waveform that looks like this. So this is our V out of omega t. So we figured out the output voltage waveform that this rectifier is going to give us, V out. It's picking out the maximum of the line-to-line voltages. And as for when the diodes are going to conduct, diode D1 is going to conduct when VA is being a maximum. Now, diode D2 is going to conduct when VC is at a minimum, or in other words, when negative VC is a maximum. But diode D2 will conduct when VC is the minimum of VA, VB, and VC. Diode D3 is going to conduct when we have VB as the maximum of the three. Likewise, D5 will conduct when VC is the maximum. D6 will conduct when VB is the minimum of the three, and likewise, D4 will conduct when VA is at a minimum. So if we go back to these curves, we have that VCB is our initial output voltage. So that means VC is at a maximum. So that means that D5 will conduct, and A is at a minimum, VCA. So that means that diode D4 will conduct. So we have D5 and D4 conducting. So in this period, we have D5 and D4 conducting. Oh, I'm sorry. So VCB. So we have VC is our maximum, VB is our minimum. So we have D5 and D6 conducting. So I made a mistake here. It should be D5 and D6. VAB is now, VA is our maximum, VB is our minimum. So VA will be D1 and VB will be D6. And then we have D1 and D6 conducting. The next VA is still conducting, so we have D1. Now VC is going to be our next minimum, so that means D2 will conduct, D1 and D2. Now in the next cycle, we still have VC as the minimum, so D2 will still be conducting, but VB is now our maximum, which means D3 will be conducting. For the next one, VB is still our maximum, so we'll still have D3, and then VA will be our minimum, so that means that D4 will conduct. So we can start to see a pattern here. So in this case, we have D1, D1, and then it switches to D2, and then D2, D2, and then switches to D3. In this next case, we have D3, D3. So we can infer that the next diode that conducts should be D5. So we have D1, D1, D3, D3. So the next two should be D5, D5. And then we have D2, D2, and this one should be D4. And then we should have D6. So essentially, we have figured out the order in which these diodes are turning on and off to rectify the three-phase voltage sources to give us our desired output, which has a DC component that gives us very little ripple and overall is a good rectifier to convert AC to DC. So we've just completed the hand analysis, and now I've pulled up an LTSpice schematic of the circuit we just discussed to verify our results through simulation. So here I have the three-phase voltage sources entered that are 120 degrees apart from each other. And the magnitude is 169.7, which is the square root of 2 times the RMS value of 120 volts. So that's the peak value of our line to neutral phase voltages. Now, I've entered a value of 100 ohms for the load resistor. And for the simulation period, I've set to 16.67 milliseconds, which is the period for a 60 hertz sinusoid. So I'm going to go ahead and run the simulation now. What we want to check is the output voltage waveform, which is the voltage across the load resistor R1. So if we probe this point here, we see the output voltage and its ripple. So it goes from a peak value of 292 volts down to around 252 volts. So we're seeing around 40 volts of ripple relative to an average value of, take this average value, we see an average value of 279 volts. Um, so we're getting around 40 volts of ripple um, relative to that average. And for the peak value, if you recall from our analysis, it should be the peak line-to-line voltage. And the peak line-to-line voltage we know is square root of 3, that of the line to neutral. So that gives us a value of 294 volts. So that's very close to the value we're seeing in simulation. So that's a good check. And the next thing we want to verify is that the sequence of our maximum line-to-line voltages that shows up at the output is correct. So we expect from our hand analysis for this first bump to be VCB. So we expect VCB to align with this first bump here. So if we measure from VC to VB, we see that indeed the first bump coincides with the maximum line-to-line of being VCB. From our hand analysis, the next hump we found coincided with VAB being the maximum. So when we probe here, we expect that this hump is indeed matching. Now for the next hump from this point onwards to this point, in our hand analysis, we found VAC to be the maximum during this period. So indeed, during this interval, VAC is the maximum. The next is VBC. Indeed, VBA is next. VCA is the one following that. And indeed, we see that our simulations match up. So this simulation confirms the results that we found from our hand analysis. And I hope you found this to be a good starting point for your analysis and your further studies into three-phase rectifiers. I hope if you found this video helpful that you could give it a like as well as subscribe to the channel if you'd like to see more videos and content like this in the future. Thank you.